Okay, ladies and gentlemen, so welcome with certain technical difficulties to our lecture Data Analytics. The scope of our lecture is Introduction to Statistical Modeling, because this is what we will be doing here, with certain focus on Bayesian statistics. In future, technical problems should be solved. At the moment, I'm not sure how, but I think there are some issues with OBS and resolutions for live streaming. However, online quality also is dubious. So, as most of you already know me, my name is Jerzy Baranowski. I reside in building C3 in room 214. You can find me on my email or through Teams at jb@agh.edu.pl. This project consists of a lecture and laboratory exercises, and ends with an exam. Lectures as lectures will be in English. All of them will be available on YouTube after uploading, so it might, as usually, take some time, but all of them will happen. Next week lecture will be online only, because I am on a late holidays after influence, like a flu got my son in proper time. Either way, the laboratory exercises are split into two parts. First part are normal laboratory exercises, so you familiarize yourself with statistical modeling techniques and using probabilistic programming language STAN that we are using, and of course Python, which you should already know. And then there will be a mini project. Approximately 5 classes will be focused on the mini project, which you will do in groups of 2. You will select your own topic, your own data, and you perform the analysis consistently with what we were doing on the lectures and during the exercises. Those projects can be rather interesting, depending on how well you get into the topics that are in it. And previously, some of those have ended as master thesis. So just were expanded on that, and it's a master thesis in the form of a journal paper. So my students have wrote papers that are already published in international journals. They are first authors of those papers, and I'm as a coordinator of those works. And that is a useful thing if you think about, let's say, PhD studies or something like that later, because it helps in recruitation, and you can also show it if you want to do some more research-oriented work after studies. So, and of course, that's the main benefit of that is because we are writing a research paper, not a thesis, is shorter, because it's like 20 pages max. In the journal template form, so it's relatively easier to prepare based on research you've done during this project and maybe expanding on that. At the moment, there are new rules regarding master thesis in our university. One single person can supervise only 4 master theses. So at the moment, from this course, I am the only one that can. Hopefully next month, Magister Dudek, that you already probably know from the your first studies, will have a PhD. His defense is next week, so hopefully he will get it, and he will also be able to supervise some thesis. So if someone would be interested expanding a project from this course as a thesis, this is an option. Up to 8 people, really. The grade will be mostly based on the project, not on the laboratories. Of course, not participating in laboratories will be noted and consequences will be drawn. The projects will be evaluated by us and by your colleagues, because we will have peer review. So each team will receive also 2 projects to evaluate with a checklist. If checklist, you have a checklist that you have to evaluate each, is the project realize those goals or not? And of course, if this evaluation would be too friendly, there will be consequences regarding the like dishonesty in grading your colleagues will be verified, and in that case, might result in reduction of the grade from the course. So I try to do it properly. And finally, there will be an exam. Generally, exam will be similar to the one we had on numerical methods. However, the last few years, I had a lot of outside interference in realization of this course, so we've dropped it only to the project. This year, I intended to do it as in a syllabus, but we'll see how it will develop during the semester. Generally, if there will be a lot of lectures missing, I won't be doing an exam. So in a form of asking you questions, because I would feel that that would be not fair for you. Okay, and then we'll just use the project grade as an exam. But we'll see how it will happen, hopefully in a normal way. Are there any questions regarding these organizational aspects? Everything is clear? Perfect. This course will be based on Bayesian statistics and Bayesian modeling. I'll try to explain to you why Bayesian modeling makes sense and in what way is advantageous over more popular typical machine learning methods, and of course in which way it is worse, because there is no ultimate solution for everything. We'll discuss how to compute Bayesian models, which is actually much more complicated than in classical machine learning situations. We'll focus on structured models, so the models that we control what comes into the model, what parameters are being, what parameters represent what, and how each variable in the model interacts with each other. And this is because this allows us model interpretability, which is very important in many applications, as sometimes when you have a model that helps you make a decision, and decision is either successful or bad, you want to know why it happened, why this model gave you that decision. And if model is interpretable, that's possible. That's why European law provided requirements for example, banking models and economical models to use interpretable models, because then you can come back to it and see what happened. And if you, for example, use a neural network, that model is not interpretable. Because there are so many parameters, so many interactions, you don't know why certain aspects do what. And if someone tells you about, oh, but there's an explainable AI, no, explainable AI doesn't work. It's just heat maps on images that make sense in cherry-picked examples and don't make sense in most of them. So explainability is not interpretability. And finally, we'll discuss model evaluation, so how to verify if our model is good. Because what we will see during this course is that Bayesian models are not models that give you just a simple answer as a number, it's 7 for example, but gives you much more, and that much more includes quantization of uncertainty. And how to evaluate if this modeling techniques gives you good results is something that requires a bit of work. We will focus on we'll have certain books that are available to us to use. One book that this is our main book. which we won't be using that much, but gives you an option to read something about Bayesian statistics. It has one very big advantage. It's free. So you can download this book from the publisher website. I will put a link on YouTube to it, or you can just look for it on Google. And this is an advantage. You can get a legal free PDF for it. Other things are not that easily available. However, this book is a bit dated regarding certain aspects. Certain aspects are okay, certain ideas are okay, most computational techniques are rather dated. And so that's why certain things are not being done anymore, which were described in this book. Much better book, however not free, is the Statistical Rethinking by Richard McElrath. This is a very good book for people that want to learn themselves. This book is constructed in a way that it includes a lot of code examples, a lot of coding exercises that will help you understand how models are being made in Bayesian practice. There is the book is kind of specific because the author works in an anthropology lab, and examples are more in that area, not technical, but more social and biological. However, these are the places where statistical modeling has most of came from most development come from there, because in biology, in economy, in sociology, you have a lot of uncertainty by default, because of like surveys come only with like 30% of answers, or people lie, or there's a lot of variance in the population. So the thing that requires statistical modeling. That's why some people came to those areas and just did their work and developed new mathematical models that were just based for that. Either way, this is a very good book. Unfortunately, it's expensive because you just it's published by CRC. Their books are generally expensive. Books in English are expensive because they can be used in any market. Books in local languages are much cheaper. And for this book, the author has constructed the collection of lectures that are corresponding to the contents of the book directly, and those very good lectures. I would risk the lectures are even better than the book, because certain things in this book are written inaccessible, especially regarding causal analysis of models, which we'll try to discuss in this course, maybe in a more clear way. But there are certain things that kind of are hard to follow directly from the book, but they are better than in the lecture. Either way, very good book. One potential issue: everything is in R. R language is a statistical language for R and Stan. Stan is universal, but R is old, and certain things in R can be irritating as a language. Like, for example, that you refer to the field of an object with a dollar sign and not a period, because when it was created, there was no periods in available table of characters. So to refer to the field of a structure, they use a dollar sign, and then when they extended the table of characters that are admissible, they've introduced the period, but it's treated as a normal character. So function called data.table is just a name. It's not a reference to a field. So like for people that are used to a modern language, it can be irritating. And of course, you have library. So you have one library when one function is called data.table, and the other one there is data_table, just to be fully clear. And you don't see the package, you don't see anything. So, but that's R. Third thing that we will be using, or this I advise you to use, is the case studies by Michael Betancourt. Michael Betancourt is a statistician, a blogger. He has his own website where he's like kind of writing a book which is being published as not published in shared is progress work, and there is this is most advanced stuff regarding new cutting-edge solutions in Bayesian statistics, Bayesian analysis, with certain quirks coming from the fact that the author is a physicist. So we'll have weird notations and focuses on stuff that are not really typically oriented for engineers. There is some stuff behind the paywall in the in his Patreon site, especially access to earlier material, to newer material, which is being then publicly shared later. Either way, very good content, but again, a lot of R, that's a minus for you, and can be hard to access sometimes. For further reading, there's a Student's Guide to Bayesian Statistics by Ben Lambert, which is what one called a second modern book for Bayesian statistics. The first one is Statistical Rethinking, which I think is better generally, but that one has this spin of self-learning, on doing lots of exercises, doing working. This is more traditional textbook. It's not bad, but I'm not a fan. Not a fan, I don't use it. And how many books on basics you can read? And there are books focused on Bayesian analysis in Python, which might be interesting for you. However, I would not go to that book directly. This is a book that helps you use numerical Python package in Python called PyMC, which is a package for Bayesian statistics. However, it helps you use PyMC, but let's say it gives you just enough rope to hang yourself, because there is less content and understanding and more function calling. There is an entire Bayesian computation ecosystem in Python. It's based on PyMC, package Avis that we will be using, which is for visualization of results, and package Bambi, which is for simplified computation of regression models, which we won't be using. And this book describes this computational environment, but not give you much for understanding. So you can create models that make no sense and you don't know why. There is also Bayesian modeling and computation in Python, which is kind of advanced version of that book. Extension to this is also free, but it is not a good book for starters. It has some solution, but you kind of can't start working on methods of Bayesian statistics directly from this book, and it is also based on PyMC, but it's freely available as a Jupyter book. So you can see how this clickable chapters, stuff like that. So there's a lot of those online. So why I'm telling you all those books? Because generally lecture is one thing. Bayesian statistics require more understanding from you than just mechanical use of tools. You can't just go and run certain models just directly. This is not something like run scikit-learn and fit logistic regression, which you do like in 5 lines at this moment. And here you need to do an analysis what actually is going on, because you have to quantify your assumptions and use them properly. Because if you don't, you get worse model than simple machine learning, or in worst case, you get model that just doesn't make sense, and you have problems with analyzing it. So We are focusing on Bayesian data analysis because of a few reasons. First of all, we focus on models grounded in probability because this gives us a natural way of handling uncertainty. Generally, all processes that are happening that we are interested in are not certain. We do not know everything. All our assumptions provide some simplification. Certain things cannot be directly measured. Certain things cannot be properly measured. In case of elections, we don't know will people go to the election or and not only how they will vote. So all those things can be a bit problematic. And using Bayesian models, we can acknowledge the fact that, okay, we don't know everything, we don't have perfect certainty about everything, and this is the measure of it that we have. So we can tell you not only what is our prediction, but also what is the uncertainty of that prediction. And that is different kind of quality. And moreover, it allows you to make some decisions or make some kind of inference, even if you have very limited data, which usually you cannot do with machine learning because it will just won't converge to a model. We want the models to be interpretable so that you can trace back what was the decision, what caused the problem, and that the model is transparent, so where the parameters come from, what are the parameters, what are the actual interaction with everything. Thanks to that, we can evaluate if our model makes sense also from the logical point of view. Because if you take your data and you put it into a machine learning model directly, it can introduce certain interactions that come directly from correlations and not necessarily represent any kind of causal relationship. So that's why we are focusing on those models, because we can do all that. Have uncertainty analysis and have transparency and interpretability. And it is important to know that really it's not the fact that one or the other category of methods is better. This is no situation. Actually, to have a sensible data scientist toolbox, you need to be able to select what proper tools are for what case. Certain cases are best for machine learning, and machine learning gives you the best results in multiple situations. However, in certain cases, you cannot use machine learning at all because you have not enough data or you have low quality of data. That's why doing data science requires you to have multiple tools, and that's why we are trying to provide you with those tools as well as possible. This semester we have data analytics, next semester we'll be doing machine learning, and we'll focus on different types of models and with different focuses. So, generally, statistical modeling and machine learning are very related fields with actually an artificial division, because what is a statistic? Formally, statistic is a function of random variables. It's a function of data. And what are machine learning models if not functions of data? You put data, you get an answer, right? You get a number. And in case of statistics, it's such a big and unwieldy field with very complicated terminology, with terminology that is internally it's not consistent internally, that certain things with different users mean different things. People understand things completely different. It's really not marketable. And that's the problem. So like machine learning is a part of statistics. AI is a part of machine learning. If someone tells you that everything is AI, and I've met people who said that electrical kettle is an AI because it knows when to turn itself off. So, but they were from Polytechnica, so that explains some things. Either way, everything is statistics, but we don't call it statistics because it's not marketable. So generally, we have this division that we have machine learning, where you put data and get numbers, and you have statistical modeling, when you put data, some assumptions, and you get numbers and uncertainty. The issue is that for certain problems, getting uncertainty is not possible because those problems are too complicated. For example, large language models. Large language models, which I'll probably explain to you in more depth next year, we are generally very specific random number generators. But we will move to that on the later date. Either way, because we have the statistical modeling and machine learning, we have two subfields of statistics that should not be put one against another, because they are kind of doing different things, and they are for different applications. You cannot say that your statistical model with uncertainty measures is better directly or in general than, for example, random forest. You cannot say that, because for certain applications, say, random forest will work perfectly, and you won't be able to create a statistical model that will make sense. However, random forest won't give you any uncertainty measure in classification. It will say, for example, healthy or sick, and it won't give you uncertainty how certain you are of your decision. Generally, statistical models incorporate probability in their analysis, focuses on something called data generating process. That's it. When we observe something, we do not observe the process itself. We never observe the entire process itself. We kind of have some kind of data. For example, if you have a cup of coffee, right? How you can measure the temperature of coffee which you have in your hand? If you don't have a thermometer. Okay. Okay. So, do you put a finger inside of it? You might. You might, okay. Then you are not measuring temperature. You are measuring sensitivity of your finger, right? You have warm or hot. Generally, you have information. It is warmer than 36 and 6 or colder. Because if you don't feel anything, it's 36 and 6. If it's colder, it's lower, okay? But this is your data is your feeling here. If you touch the cup on the side, you have also the cup dynamics, right? And also the process of the coffee is cooling all the time, right? So you have the process of temperature at certain moment. This is the data generating process of what's going on here, right? You get the information. You can incorporate certain assumptions to the model, right? For example, when I have a coffee in a cup and it's liquid, we can be certain that it's over 0 degrees centigrade, right? Also, because it's not boiling, it is under 100 degrees centigrade. So we incorporate our assumptions here. Because the cup is not very hot and we can hold it by hands, probably it's lower than 100. So we can introduce additional assumption, additional observation to incorporate our prior knowledge. However, when we are discussing what this cup has, formulating this assumption of the model, we are creating certain interpretability. We now understand what do we mean by putting a finger in a coffee, right? And we know what influences what in it. If someone is, for example, welder, then that person has much lower sensitivity on heat on their hands, right? Because like they are working with very hot metal, and sometimes they even have nerves damaged through multiple burns on their fingers. That can happen. So there's a lot of potential aspects that need to be considered in the data generating process, because actual process, temperature of the coffee that is evaluating over time, is measured through a proxy of some kind. And in the more complicated process, the more proxies we have that reduce information, introduce their own spin on it, increase uncertainty of that, etc., right? Okay. Generally, statistical models are kind of considered like regression models to create some kind of fit to the data, but not only that. But like regression is a keyword that returns in these situations. However, it can be very complicated, very multi-level regression that is not really typical curve fitting that we have. And of course, statistical models are not limited to linear, because you can do a lot of stuff by specifying appropriate functional relationships. On the other hand, machine learning is something that is much less transparent. So we do not use traditional parameters that, like in the regression, that corresponds, which is like what is the linear effect of certain variable on entirety. You don't have initial structure like it's a linear combination of variables. You have, let's say, you can have a neural network, you have a decision tree, you have a random forest, you have, let's say, gradient boosting algorithm, stuff that is more and more complicated without really initial structure that corresponds to relationships. You usually do not focus on individual variables. In our case, we've just measured the temperature here and we try to understand what the temperature is going on. In machine learning, you generally train test split and then put it into a proper model and run it. Do not considering what are the relationship here. You don't try to understand it too much. If you go through images analysis, you usually add convolutional layers. It's rare that the model is pre-processed to get some features from it by understanding what's going on. However, that does not make an issue that machine learning models cannot learn from data. They can, and they can capture a lot of stuff without, especially if you have a lot of data. With my PhD student a few years ago, we did an experiment, that's a byproduct of his PhD, that using the camera, single molecular camera, he did tests of localizing depth perception in the model. We had LiDAR data, which gave us 3D mapping of the terrain, and we have a camera with object detection. And the problem always in this situation is how to locate how deep is the object regarding the camera if you do not use LiDAR data. But with having that information about the depths, we could teach the neural network to determine these parameters. Why it worked? Why from one single image it was able to get the depth despite the fact that there's only one camera. So monocular, right? Because our neural network has learned the optics. Because there is a science called photogrammetry in neighborhood faculty of geodesics, where they generally using photos, they can, and knowing what kind of lens was used, what kind of lens parameters there are, they can reconstruct geometrical information from the photo, because they know what kind of curvature is there. And neural network can learn that if provided enough data. The different question that we never moved through on, because there was no interest in Aptiv for that, if we would use the photogrammetric knowledge to extract some features from the object, from the photo, using the information of the lens, how much it would improve the work of the neural network. But that's different aspect. Either way, machine learning models can learn from the data to capture certain behaviors quantitatively, not qualitatively. So not understanding the process, but quantitatively, so giving you the same numbers as the process gives for the same inputs. And that's the modern AI actually how it works. Okay, and machine learning does not rely on additivity because it produces more complicated models. Machine learning is better, especially in the situations when you have high signal-to-noise ratio. What does it mean? It means that the data is much more significant, actual information of what it is much more significant the data than any kind of disturbances. So for example, data that has very high signal-to-noise ratio are images. Because in a photo, you can see a structure. Even if it's blurry, you can see that it's a car, right? Of course, there are issues with this dog under bars with shadow that looks like a tiger, right? But generally, you can get a lot of image just by looking at it, because there's a very strong structure. The same is with speech, with sounds, because sounds have of people speaking sound a very specific way. The same with text. Text is very structured. So even if there is a typo, the model can handle that because it can handle it from the structure that's coming down. However, for example, electrical signals, social signals, those information from the surveys, biological observations, those things can have a very high noise ratio because the process of measuring can be very complicated. Like, for example, when you use a ultrasound on a human, you don't see directly what's inside, right? You see only those shadows there that you need a specialist that will be able to handle that and to read what's going on in the ultrasound. So this is a very high noise to signal ratio, or very low signal to noise, and that's a problem. So like visual sound recognition, language translation, this is a very a good place for machine learning. Tabular data, not necessarily. In case of data that come in tables, machine learning, especially neural networks, do not work that well. Generally, we have some kind of a black box approach that if it's not a problem, because we don't know how to do it a different way, machine learning is perfect. So understanding of images, we don't know how to mathematically do that. That's the problem. That's why we use millions and millions of parameters, because we do not know how human brain works. Human brain does not work like an artificial neural network. It never did. It was a marketing ploy. But it's name stock, so people use it. But it was analyzed that to do things that humans do using available mathematical apparatus that we have, human brain computing power is not enough. we wouldn't be able to do things we do if it worked this way. So in order to work, human brain has to work a completely different way. Create some kind of data processing heuristics that we don't know how to work. But if we want to do stuff that we don't know how humans do, we can use black box, because we get something, right? Also, if we have very large data sets with very large number of features, so like images or long specific signals, perhaps using the machine learning also will work better, because creating interpretative relationship between multiple features going in thousands might be very, very difficult. On the other hand, statistical modeling can handle small data sets, because besides data, you can introduce assumptions to the model. So having this assumption on the contents of the cup, right? First of all, if we introduce a data that the coffee has 1,000 degrees temperature, the model will discard the data, right? It will not influence the inference. In case of machine learning model, it might do weird stuff. You can compensate for things that are impossible, introducing what things are likely to happen, introduce so-called prior knowledge to the model, and that will allow you to compensate for the actual lack of data. Statistical model with good assumptions can provide you with some kind of insight even without data. Machine learning without data does not exist. Statistical models provide us with uncertainty estimates. Even more, they provide us with full probability models, but full probability models in dimension greater than 1 are kind of hard to understand. So that's why we use estimates. They are transparent and they allow us to investigate relationship between features, investigated what the actual influence of predictor is. And for example, we can analyze the model and find a situation that what model gives is counterintuitive or even completely contrary to established knowledge. So then we have a situation. Either physics doesn't work and we should get a Nobel Prize, or there is something wrong. And introducing that here allows you to handle the situation, provide some kind of corrective action to verify the experiment, to return to drawing board to see what's going on. And for example, if you have a large uncertainty on your prediction that is contrary to the physics, then maybe there's something wrong, right? Okay. Generally, machine learning might need more data for the same problem to get comparable results. And because of prescribed structure of statistical models, we can introduce what kind of relationships there should be there, because they come from logic, right? Or science or earlier research or stuff like that. However, we cannot, statistical model will not do it for us. So it won't be able to establish relationships that are not there if we do not put their possibility in the model. Machine learning actually can. They can capture the very complicated multidimensional relationship between variables. We will just have very big problem to get out from the model what those relationships are. So it will quantitatively get you the right results, but you won't know why. And generally, machine learning can be a better predictor or classifier numerically, but in the uncertain cases there will be more issues because they will go to one way or another. So, like for example, there was a few years ago, there was a lot of enthusiasm, or Google established new model for cancer detections from photos that has very high accuracy rate. It was very nice, however, actual problem in analyzing cancer photo is not to see, oh, there's a cancer in this photo. This is something that doctors actually handle rather well. The problem is to have a model that will be very certain there is no cancer in this photo. Because in that situation, a person that is sent to further diagnostics that has no cancer blocks the system. Because the system has very limited throughput. It can handle only so many people. So if people will be sent to from screening variables to further diagnostics without right issue, there will be a problem. So, and that model was not very good at discriminating those situations. Machine learning, because it's easier and it's more marketable, has some very vocal advocates. Why neural networks are the only solution? Because like, it sounds very nice. There's a lot of marketing put into the machine learning, especially deep neural networks. When people tell you about cortexes, attentions, chains of reasoning, which are actually either vector function of a nonlinear vector functions or simple Markov chains, exploration of random spaces, things that have very good mathematical grounding, but much less marketable. And people will tell you that machine learning and AI is the future, and most of people that say you that are people that didn't really work with AI in their practice. So like for example, you say Bill Gates says AI will take jobs, right? And then you ask ChatGPT to answer some questions and you know that it won't be that fast, right? A corporation would love AI to take jobs, but there will be a return in some time. Because just, and on the other hand, statistical models have this issue that statistical computation requires a lot of numerical work. And in large data sets, that can be problems. That can lead to problems because generally the advantages in large data set analysis in machine learning come from very efficient dropping of data and scalability of certain computation. And those things cannot be easily done in probabilistic computation. Because I'm not sure, do you know how learning of neural network, deep neural networks works currently? Do you have some kind of introduction to that? Backwards propagation is a method of computing derivatives. However, the problem is that computing derivatives is one thing, but how to use that knowledge in order to improve weights. Because backward propagation gives you gradients. So in optimization, you know where the function decreases. The problem is that in order to evaluate the gradient of the loss function through the network through backpropagation, you need to compute how that for each of data points in your data set, right? Because generally loss function in neural networks is sum of least squares with some kind of like modifications, but generally it's separable into components from each individual data point. The main idea currently working is something called stochastic gradient descent, which works like this, that you compute gradients on a subset, randomly sampled subset of data, and you change that subset every iteration. That's why it's numerically feasible, because it requires much less computation. That's why no advanced optimization methods are being used in machine learning. You've learned on optimization methods about BFGS algorithms and transfusion algorithms perhaps, which are not used there because they require you to compute the second derivatives and they cannot be computed with stochastic gradient descent efficiently. So generally that computation is very expensive, not usually, so stochastic gradient descent allows you to drop that. And but that unfortunately reduces you the influence of each of data points, which is necessary for statistical models. So that's why statistical models really need to use all of your data, but probably will require some kind of data reduction to work properly. Okay. So we use statistical models when we need the uncertainty estimates. Because, for example, we want to know how likely is that something will break down in next week. We don't need the answer, oh, in 90% it won't. We need to know exactly that in 10% it will. And machine learning will give us, oh, no, it's okay. It's over threshold, it's okay, right? And we will do an example in the next lecture on utility function, that what are the costs of uncertainty that you are able to analyze having the data from, having the costs of, having the uncertainty of the model, you can then establish how costly would be the results of model not being wrong, but of certain scenarios. Of course, we can use statistical models when signal-to-noise ratio is low, because we can compensate that by proper modeling of data generating process. Because having that information in your model allows you to understand the structure of the noise. Because sometimes signals are lower than have lower amplitude than noise by the design. The best example is GPS system, where actual data that comes from satellites is below the level of the noise. But because it has a very specific structure, and you know that structure, you can decode that and get it. Despite the fact that there is a lot of noise, you can still get, and this noise can be larger than actual data, you can get the data and get information from GPS. And we are interested in effects of individual variables. We want interpretability, and we have smaller samples, so we need to compensate for that with prior knowledge. Machine learning is an inverse of that case. That is that we have large signal-noise ratio, we have large data set, we don't have much randomness. Machine learning doesn't like randomness, really. People will say, well, signal-to-noise ratio in the images isn't a problem. However, if you have noise in the labels, there starts problems. If you have, for example, you have neural network and you learn it with the data that has mislabeled images, for example, then it is shown that by rather simple changing of labels, you can drop the accuracy below 50%. So those models don't like mislabelings, and actually statistical models can handle mislabeled data, but you need to know what you're doing. Generally, you need a lot of data, because if you are not giving this structure, it has to find the structure by itself. You want numbers, actual predictions or classification directly, and you don't need uncertainty. And okay, and we are focusing on Bayesian statistical modeling, because there are two methods. There's Bayesian statistical modeling and frequency statistical modeling. Frequency statistical modeling is something called classical statistics. In general, it is very easy for very simple cases, and for difficult cases, it's absolutely hard. Bayesian modeling is hard for everything, but now numerical computation allows to skip that hard part. Because frequency statistics was the only thing that was possible to use using analytical computation in practice. But now we have so efficient methods that we just don't need that. Generally, in Bayesian statistical modeling, we work on the following scheme. We set up the full probabilistic model of data generating process. So we influence everything that we can in our model. Then we use the data that we observed to, using that model, create a conditional probability of, for example, parameters of that models to get an inference what's going on. And then check and evaluate model as much as necessary. As I mentioned, we have the aspect that frequency statistics is different. Not only that one is harder or not. There are, let's say, philosophical differences. In case of frequency statistics, we assume that the process that we are considering is fixed. Let's say like it's what we are interested in is a number. This number is a fixed number, let's say 7, and we want to estimate that number. And we consider how data, or what kind of data could be generated by this given number. So we say in frequency statistics that process is fixed, but data is uncertain. In Bayesian statistics, it's opposite, because the data that we have is the only thing that really we have. We have data. We have concrete numbers that were measured, right? Everything else, we don't know what's going on, but data has happened, is available. This data not necessarily is actual value of the phenomena, but that's why we have a data generating process. To see how that data was created, how it was created. So what kind of model parameter configurations would lead us to this data. So our model is uncertain because we don't have a certainty about parameters of the models, because from the data that is an actual tangible thing that we know, there are multiple ways that this data can could be created. So our uncertainty of model parameters covers what was the possibilities that would create that and how likely those possibilities are. Okay? Second thing, in frequency statistics, we work on data only. We have data, and from that data, we infer about the process. In Bayesian statistics, we introduce something called prior knowledge. That is what we knew about actual parameters of the model before we collected the data. For example, we knew that coffee in a cup is between 0 and 100 degrees centigrade, right? Because it's a liquid. If a child touches your coffee, it's, oh no, it's 1,000 degrees, right? In Bayesian model, that data is compensated by the prior. No, it's not. In frequency statistics, if we did not discard this data point because of some reason in analysis of outliers, then it is being then it's being introduced to estimator, And for example, we get, the second measurement will be 30 degrees by an adult, or 40. Then the average of those two samples would be around 500, right? That's a problem. And introducing prior knowledge, we can compensate for multiple things, and we can direct our model into proper places that would allow us to improve computation and also handle the issues that are happening, right? But, as I said, data is fixed. Everything else is uncertain. So how we capture this uncertainty? We capture this uncertainty by the fact that everything in Bayesian model has its own probability distribution. Generally, we have a model that incorporates uncertainty in all of the parameters and their relationships, and by conditioning it on data, so limiting it kind of to the data that was observed, gives us more complicated or less complicated probability distribution of how each parameter is entire vector of parameter is distributed in the admissible space. Main advantage, the Bayesian statistics is a very specific situation because this is a branch of science that was actually fought. There were a group of people that were aggressively fighting against adoption Bayesian statistics in any kind of mathematical statistical analysis. Because their argumentation was that introducing the prior knowledge, we introduce the subjectivity to the model. Because one person can think one thing, the other person can think other thing, and it will not be fully objective model that everyone will get exactly the same results, and in frequentist statistics you get. But more important question is it important to get exactly the same answer or to get proper answers? And there's a very nice book that describes this war. It's called The Theory That Wouldn't Die, that describes the entire history of Bayesian statistics, which, as its name suggests, was created by Pierre-Simon de Laplace. And so Thomas Bayes just gave an idea and gave an example of throwing apples on the table behind him, something like that. Everything was done by Laplace. Frequentist statistics were also done by Laplace, who kind of formulated all the main ideas that are being used later because he was not able to compute analytically anything with Bayes. But, for example, was able to compute the mass of the Saturn using available data, and his measurement fit after verified with modern technology was within the actual result was within the interval of confidence that was provided by Laplace. So this is something that worked. And generally, the Bayesian statistics won because it's won. It's not like it's the debate anymore. No, Bayesian methods won. They are being widely adopted in multiple branches because they work. And they allow you to do things that classical statistics won't allow you to do. For example, when you have a young driver and you want to give them the insurance rate, right? What is the probability that they will have crash? Right? They never drove before. They have a driver license for a week and they bought a car. But you have a prior knowledge about other young people and how they drive, right? So you have adjustment of rates, for example. Or they were using Bayesian statistics to find lost nuclear bombs. Because during 50s and 60s, there were planes that were flying with nuclear bombs during routine flights during Cold War, right? And there were, 17 cases that the bomb just dropped and fell into the ocean. And finding that at the bottom of the ocean is not an easy case. And they were using Bayesian statistics to narrow areas where the bomb can be. And that's not possible to do with frequentist statistics because, well, not enough cases were registered to happen, right? There is no data, there is no solution. This is a very nice book. This is a popular science book. You can find it on Audible if you are using it, or if you're not using it, there's like a free trial for a month, so you can listen to that. Or you can buy it from. It's a very, very nice book with lots of examples from history. Enigma was the all work of Turing was based on Bayesian statistics, which is in Poland it's less noticeable because we speak only on the achievements of Polish mathematicians in the development of Enigma, which is not as substantial as people think. Okay. Enough. Enough for today. Next week, as I said, there will be an online version of the lecture. I will record it in advance and it will be in the time slot of this lecture because I won't be available. Are there any questions to this lecture? Okay, so thank you very much. Have a nice weekend.